Hello everyone. In this video, we'll look at one of the important equations of electrostatic fields, which is Poisson's and Laplace equations. We will start looking at the equation from Gauss law, that is first equation of Maxwell's of electrostatics is represented as divergence of electric flux density equated to volume charge density. Now this equation is useful in solving some of the electrostatic field problems where flux density and volume charge density are related. Now, the most common thing for the practical measurement we have is the voltage or potential. Now we are going to rewrite this expression in terms of potential function V. So we have to look at how to take the substitutions for flux density and electric field intensity from the known equations. Flux density is epsilon times electric field intensity, and electric field intensity can be written as negative potential gradient. By using these two relations, we are going to rewrite this Maxwell's first equation of electrostatics or point form of Gauss law in terms of potential function, because there are instruments readily available to measure potential like voltmeter, but to measure the electric field intensity or electric flux density by using measurements is little complicated. So to make it simple, we are going to rewrite this equation in terms of potential function, which is more useful in solving electrostatic field problems like the examples of capacitances we will look at in further videos. So when we substitute this flux density D as epsilon times E, the equation can be written as divergence of epsilon E vector equals rho V. Now, when we apply this divergence to E vector and epsilon, we should know what is the nature of this epsilon. The epsilon talks about the medium characteristics, which is the permittivity of the medium. We can write epsilon as epsilon naught multiplied with epsilon r. And we should know whether this epsilon r is isotropic or homogeneous, which means if this epsilon r is constant with respect to xyz and also in all three directions, then we can assume this epsilon is constant. That happens only if the medium is isotropic and homogeneous. Also, the variation of epsilon should be linear in nature. So in such case, the isotropic medium concerns in all directions, the value of epsilon is constant, and homogeneous medium talks about the value of epsilon at each and every point around the medium is same. In that case, we can take epsilon constant outside this differentiation of del, and we can rewrite this equation as del dot E equals rho V by epsilon. And we can replace epsilon as negative potential gradient into this equation. We'll get del dot minus del V equals rho V by epsilon. And we can even take the negative sign to the right hand side, and we have divergence of potential gradient in the left hand side. So this function del dot del V or divergence of gradient of potential function, we can write in terms of del square function, where this del square is the Laplacian operator, which is divergence of gradient can be written as Laplacian operator del square. And we can write the expression for del square in all the three coordinate systems accordingly. Now we can write the Poisson's equation in terms of Laplacian of V as del square V equals minus rho V by epsilon. Next, let us look at another special case of this Poisson's equation, which is Laplace equation. We can consider if the medium or the region is charge free, which means if there are no free charges present in this medium or region, then we can assume rho V is 0, and the Poisson's equation will take the form del square V equal to 0. This equation del square V equal to 0 is called Laplace equation. Now we have Poisson's equation and Laplace equation in terms of the Laplacian operator del square. We can write how this Laplacian operator can be written in rectangular system, cylindrical system, and spherical system from the known equations of divergence and gradient formula. So let us look at the gradient and divergence formula in rectangular system. The gradient of V indicates variation of V with respect to x in x direction, with respect to y in y direction, and with respect to z in z direction. And divergence function can be written as dou by dou x of x component of vector A and dou by dou y of y component of vector A and dou by dou z of z component of vector A. Now we need divergence of gradient of potential function, which means we are taking divergence of the gradient function. So this gradient is the vector for which we have to find divergence. So in that case, this x component will be the x component of this gradient function, and y component will be this y component of gradient function, and z component is the z component of this gradient function. By applying this, we can write the Laplacian as second order differentiation of v with respect to x, y, and z correspondingly. So we will get dou square v by dou x square and dou square v by dou y square and dou square v by dou z square for del square v. If we equate this to minus rho v by epsilon, this is the Poisson's equation in rectangular system. And if we equate this to 0, we'll get the Laplace equation in rectangular system. Similarly, we can write the expression for Laplacian or divergence of gradient of potential in cylindrical system and spherical system as well. So we have the gradient formula for cylindrical system and divergence formula for cylindrical system. If we apply the rho component, phi component, and z component corresponding to this, we can get del square function as given here. We can equate this to minus rho v by epsilon for Poisson's equation and equate this to 0 for Laplace equation. Similarly, we can get the expression for divergence of gradient of potential function for spherical system. And this is the equation for del square v. And when we equate this to minus rho v by epsilon, we'll get Poisson's equation. Equating this to 0 gives Laplace equation. Thank you for watching the video.